So welcome to some aspects of tree-varied Fourier diffusion. This is a joint work with Andreas Greven, and the paper can be found on arXiv. The aim was to construct and study processes for the evolution of branching population together with the genealogy of individuals which are currently alive. So this is important. The suitable state spaces of such processes are already present in the literature, and we are interested in properties of branching processes which can be lifted to the tree-varied setting. Okay, this is a picture of a continuous time Galton-Watson process together. So we have the process and together with its tree, and from the tree we can of course read off the genealogy of the Galton-Watson of this population at any time. So the genealogy here is evolving, and the genealogical trees can be encoded here by ultrametric spaces where U is the set of leaves and R is the genealogical distance. So just we think here of twice the time to the most recent common ancestor of two individuals. Okay, and the encoding is of course up to some relabeling unique. So Fourier's branching diffusion on the non-negative real line is a process which solves the stochastic differential equation, and it can be obtained as a weak limit of nearly critical Galton-Watson processes xn. Okay, and so these are the conditions of the process, and what we do is we rescale the total mass by n and speed up time by n as well. And if then the initial conditions of so rescaled process converge, then also the processes converge to the solution of the stochastic differential equation. It is known that the Laplace transform of z has the following form. The Laplace transform is e to the minus z times the function ut of lambda, and ut is a solution of this differential equation. And from this we already can see that this is of course the distribution is infinitely divisible, and in the critical case, okay, u has this form, and the Levy measure can also be given, is given by this mu. Okay, the state space of our process is are the ultrametric measure spaces. An ultrametric measure space is a triple consisting of completely separable ultrametric space, where we think of U as the individuals and of R as the genealogical distance between individuals. And mu is a finite measure on the Borel sigma algebra. Two such spaces are called equivalent if there is a measure preserving isometry between the supports of the measures. And okay, one mu prime is the image of mu under this isometry. The equivalence classes are denoted by square brackets, and the set of all ultrametric measure spaces is denoted by U. The set of ultrametric probability measure spaces is denoted by U1. Any element of an ultrametric measure space with positive total mass has a polar representation where we decompose the total mass and normalize the mass of the ultrametric measure space to obtain the probability measure here. Okay, all elements with null measures can be identified in this space U. Okay, on this, okay, it is known, was shown by Greven, Fafaluba, and Winter, and then by Glöde, that these spaces are Polish. On U, one can define suitable separating test functions and generators and so on. And the generator in our case will be of the following form: is the growth part and a branching part. And all this gives rise to a martingale problem. And this martingale problem can be shown to be well posed. The solution of this martingale problem has the Feller property, the strong Markov property, and also a version with continuous path. And this version with continuous path is what we call the U-valued Feller diffusion. The proof ingredients of this theorem are particle approximation, and for uniqueness, we use the Feynman-Katz duality. There is a close connection to the classical Feller diffusion and trivalent Fleming-viot processes. And it is as follows. So if we have the trivalent Feller diffusion, we can decompose it in the total mass process and the genealogy process, okay, which is just this, this Ultrametric probability measure space. And it can be shown that the total mass process is an autonomous process and is given by the classical Feller diffusion. On this autonomous process, we can condition the genealogy process, and this is given by the time inhomogeneous trivalent Fleming-viot process, which was studied by Greven, Traffelhuber, and Winter in the homogeneous case. Okay, from this connection, we can read off, for example, that ut is for all t positive in the space, in the compact ultrametric measure spaces. Okay. We denote two subspaces of ultrametric measure spaces by UH and UH with this index here, and call those H trees and H forests. And H trees are those ultrametric measure spaces where the distance between a pair of individuals is strictly less than 2H, and here it is less or equal than 2H. We can define an operation on these spaces, and this operation is called h-concatenation. So we can concatenate two elements, U1 and U2, to obtain a new element in the H forests. Okay, so here is an extension of the two metrics to the direct sum, and this is an extension of the measures to the sum, so like it is described here. Okay, for an element U in U, we define its H top by, I just showed the picture, so given an ultrametric measure space, its H top is given by, we just cut off the tree at height H or depth H, and connect all the trees that we have cut off here. So this is an H top, and Greven, Glöde, and Rippel have shown that each element, for each element U and H positive, one can write the H top as a concatenation of H tops, of H trees in, okay, with some index set IH. Okay, so the infinite divisibility was introduced for such trees, was introduced by Greven, Glöde, and Rippel, and random variable U is called infinitely divisible if for each N and each H it can be written as a concatenation of IID elements in this set of H forests. Okay, this is, and the result about the Feller diffusion is the following. So if UT is U-valued Feller diffusion, then for each t, the random variable ut is t infinitely divisible, and its Levy measure can be computed. So the t infinitely divisible is the case that we require this to hold, but only for all h between 0 and t. Let me conclude with this slide. So there are many more, of course, known properties of the classical failure diffusion, and many of those properties can be lifted to the case of the trivalent failure diffusion. And with this, I conclude my talk.